Imagine two of the darkest objects in the universe moving toward each other. Neither produces light of its own. Both contain enormous mass compressed into incredibly small regions. Their gravity is so intense that once anything crosses their event horizons, it cannot return. Now imagine these two black holes trapped in orbit around one another. At first, they may be separated by millions of kilometers. But slowly, something extraordinary begins to happen. They start losing orbital energy. And that lost energy travels across the universe as something predicted by Albert Einstein more than a century ago. Gravitational waves. These are not ordinary waves moving through space. They are ripples in spacetime itself. As the two black holes orbit each other, they continuously disturb the geometry of spacetime around them. Those disturbances travel outward at the speed of light. And because the system is losing energy through gravitational radiation, the black holes can no longer maintain the same orbit. They begin spiraling inward. This stage is known as the inspiral. At first, the process can be relatively gradual. But as the distance between the black holes decreases, their orbital speed increases. They circle each other faster. The gravitational waves become stronger, and the frequency of those waves rises. The final moments become incredibly violent. Two black holes that may each contain many times the mass of our Sun can orbit one another multiple times per second just before merging. But here's where our everyday intuition begins to fail. We often imagine black holes as two giant spheres smashing together. That's not really what is happening. A black hole's event horizon is not a solid surface. It is a boundary in space-time, the point beyond which information can no longer escape to distant observers. So when two black holes collide, there are no solid surfaces crashing into each other. Instead, two extremely distorted regions of spacetime become one. As they approach their final orbit, their event horizons ultimately merge into a single horizon. For an incredibly brief moment, the newly formed black hole is highly distorted. It is not yet in its final stable state. And during this merger, an astonishing amount of energy can be released as gravitational waves. Consider the first direct gravitational wave detection announced by LIGO in 2016, GW150914. Scientists concluded that two black holes, with initial masses of roughly 36 and 29 times the mass of our Sun, had merged. The final black hole contained about 62 solar masses. So what happened to the remaining mass? Approximately 3 times the mass of our Sun was converted into gravitational wave energy. Not over millions of years. The strongest emission occurred in a fraction of a second. For that brief moment, the power carried away by gravitational waves was extraordinary. And yet, if this happened near you, the danger wouldn't come from hearing some enormous cosmic explosion. Gravitational waves are not sound waves traveling through air. They stretch and squeeze spacetime itself. By the time waves from distant black hole mergers reach Earth, however, their effect is unbelievably tiny. Detecting them requires some of the most sensitive instruments humanity has ever constructed. This is where LIGO, the Laser Interferometer Gravitational Wave Observatory, comes in. LIGO uses long laser interferometers to detect minuscule changes in distance caused by passing gravitational waves. When GW150914 reached Earth, the change LIGO measured was smaller than the width of a proton over kilometer-scale detector arms. And the signal had traveled for more than 1 billion years before reaching us. Scientists often convert gravitational wave data into frequencies humans can hear. The final inspiral and merger produce a characteristic rising signal sometimes described as a chirp. That tiny chirp represented one of the most violent events humans had ever detected. But the collision doesn't end at the instant the horizons merge. The newly formed black hole initially remains distorted. It needs to settle down. So it undergoes a final stage called ringdown. Think of striking a bell. After being struck, the bell vibrates at characteristic frequencies before becoming quiet. A newly merged black hole behaves somewhat similarly, not by vibrating like ordinary material, but through oscillations in its gravitational field and spacetime geometry. As it settles, it emits additional gravitational waves. Eventually, the distortions fade. What remains is a larger, rotating black hole described, in the standard astrophysical picture, primarily by its mass and spin. The shape of the inspiral, merger, and ringdown signals allows scientists to test Einstein's general theory of relativity under some of the strongest gravitational conditions available in the universe. But another question remains. How do two black holes get close enough to collide in the first place? There are several possibilities. Some black holes may originate from pairs of massive stars that live together as binary systems. Both stars eventually collapse, leaving two black holes gravitationally bound to each other. Other mergers may occur in extremely crowded environments, such as dense star clusters, where black holes can encounter one another and form new binary systems. And potentially, supermassive black holes can approach one another when their host galaxies merge. In fact, astronomers expect galaxy mergers to eventually create systems containing pairs of supermassive black holes. Over cosmic timescales, some of those systems may also merge. Today, gravitational wave observatories have transformed black hole collisions from mathematical predictions into observable astronomical events. We can detect objects that emit little or no ordinary light simply by measuring how they shake spacetime. And future gravitational wave observatories may allow us to detect even more massive black hole mergers across enormous cosmic distances. So what happens when two black holes collide? They don't simply smash together like two planets. Their orbit accelerates. They radiate energy through gravitational waves. Their horizons merge. Spacetime itself violently changes shape. And after the final ring down, one larger black hole remains. For billions of years, these collisions happened silently from humanity's perspective. Now, for the first time in history, we have learned how to listen to their gravitational signature. And every new signal gives us another glimpse into a universe that cannot always be seen with light.